When you hear teleportation, you might think of Star Trek or Harry Potter. But what's the real deal with teleportation in the world of physics? First off, let's clarify what we mean by teleportation. In the realm of quantum mechanics, it's not about zapping people from one place to another. Instead, we talk about quantum teleportation, a fascinating process where quantum information is transferred from one particle to another without moving the particles themselves. Sounds like something out of a sci-fi movie, right? Now, this hinges on a phenomenon known as quantum entanglement. Imagine this. Two particles become so deeply connected that the state of one instantly influences the state of the other, no matter the distance between them. This isn't just theoretical, it's been proven in labs with photons creating what we call entangled pairs of qubits, the basic unit of quantum information. Recently, scientists have even managed to perform almost perfect quantum teleportation, overcoming environmental noise that typically disrupts quantum states. This breakthrough is not just cool, it's a game changer for technologies like quantum computing and secure communications. You might wonder, how does this help us? Well, in quantum computing, entanglement links qubits across vast distances, allowing for much faster processing speeds than classical computers. It's like upgrading from a dirt road to a hyperspace highway. In the world of security, quantum entanglement fuels quantum cryptography. This includes techniques like quantum key distribution, which helps in creating ultra-secure communication channels. The security here isn't just robust, it's governed by the laws of physics themselves. But let's circle back to teleportation. While we're not teleporting physical objects yet, the ability to transfer quantum information instantaneously offers a glimpse into potentially revolutionary communication methods. Perhaps even something as wild as faster-than-light communication could one day move from science fiction to science fact. In conclusion, while we may not be teleporting ourselves to Mars anytime soon, the realm of quantum teleportation opens up a universe of possibilities that could reshape how we compute, communicate, and understand the very fabric of reality. Let's address the burning question. How close are we to achieving teleportation as we know it from science fiction? Quantum teleportation has seen significant advancements in recent years. Here are some of the notable achievements. First, let's talk about photon-based teleportation. Scientists have demonstrated quantum teleportation using electromagnetic photons to create remotely entangled pairs of qubits. This is a crucial step for transmitting information in semiconductors. Next, we have long-distance teleportation. There has been success in teleporting high-fidelity quantum information over a total distance of 44 kilometers, or about 27 miles, with a fidelity approaching 90%. Moving on to satellite-based teleportation, researchers utilizing the low Earth orbit Micius satellite have teleported quantum information over distances exceeding 1,200 kilometers. However, the rate of this quantum teleportation system has not yet reached the order of hertz. It's important to note that quantum teleportation is not like the teleportation often depicted in science fiction. Teleporting physical objects, especially complex ones like humans, presents significant scientific and technical challenges. First, we have the quantum uncertainty principle. This principle in quantum mechanics suggests that the more accurately an object is measured, the more it is disturbed by the measurement process. This makes it difficult to obtain the exact state of an object for teleportation without altering it. Then, there's the complexity of living organisms. Living organisms have multiple degrees of freedom, and teleporting them would require teleporting all these degrees of freedom simultaneously. This is a monumental task given the complexity and number of particles involved. Added to this are the technical limitations. Current quantum teleportation experiments have achieved accuracy over distances up to 27 miles for quantum information, not physical objects. The scale of this technology is still very small compared to the complexity of teleporting entire physical objects. Lastly, we can't ignore the philosophical challenges. Even if it were technically possible, there are philosophical questions about identity and consciousness that arise with teleporting living beings. Would the teleported individual be the same person or merely a perfect copy? These questions remain unanswered. But what about other theoretical methods of teleportation? There are several that have been proposed and explored in science and science fiction. One such method is wormhole teleportation. This involves relocating your body to another place through a wormhole or a similar construct. Wormholes are hypothetical bridges in space-time that could potentially connect distant points in the universe. Another method is molecular disassembly and reassembly, popularized by Star Trek. This involves disassembling your molecules, beaming them somewhere else, and reassembling them in the same configuration. Lastly, there's scanning and reconstruction. This method involves scanning your body, transmitting the information to another location, and using it to build an entirely new body out of different materials. While these methods remain largely theoretical, they offer fascinating glimpses into the possibilities that lie ahead. Let's explore another quantum marvel, superdense coding. This quantum communication protocol allows two classical bits of information to be sent using just a single qubit. Intrigued? Let's break it down. First, we need to understand the key players in this quantum dance, Alice and Bob. They share a pair of entangled qubits in one of the maximally entangled states known as Bell states. This entanglement is the secret sauce that makes superdense coding possible. So how does it work? It starts with preparation. Alice and Bob each hold one of the entangled qubits. Alice wants to send two classical bits of information to Bob. Depending on the bit she wants to send, 0001, 10, or 11, she performs a specific quantum operation on her qubit. This operation changes the state of her qubit without disturbing the entanglement. Next, Alice sends her single qubit to Bob. Here's where the magic happens. Because the qubits are entangled, Bob's qubit is instantaneously affected by Alice's operations. By performing a measurement on both qubits, Bob can determine which of the four possible operations Alice performed, thus decoding the two classical bits of information. The beauty of superdense coding lies in its efficiency and security. Since Bob needs both qubits to decode the information, any eavesdropper trying to intercept the message would disturb the entangled state, alerting Alice and Bob to the presence of an interloper. But how is superdense coding different from classical communication? For starters, it allows for a higher information density. In classical communication, one bit of information is transmitted per signal unit. With superdense coding, two classical bits can be transmitted using just one qubit, effectively doubling the information density. Moreover, superdense coding relies on quantum entanglement, a property that doesn't exist in classical physics. These entangled particles remain connected, so actions performed on one affect the other, no matter the distance between them. Lastly, the security of superdense coding comes from the nature of quantum mechanics itself. Any attempt to eavesdrop would disturb the entangled state, making this method inherently secure. Classical communication systems require additional encryption methods to achieve similar security levels. In essence, superdense coding can effectively increase the bandwidth of a communication channel. For example, a two-way quantum channel with bandwidth B can be turned into a one-way classical channel with bandwidth 2B using superdense coding. As we continue to explore the quantum realm, innovations like superdense coding show us that the future of communication is not just faster and more efficient, but also fundamentally more secure.